Okay, so number 48 says the net force on the 1 nanocoulomb charge is 0. What is Q? And so what we can do first is we know that the net force is 0, and that's equal to the force of, if we label each of these particles, we'll call the one in the middle 1, the one on the left 2, the one on the right 3, and the one on the top 4. Net force will be equal to the force of 2 on 1 plus the force of 3 on 1 plus the force of 4 on 1. And so first let's find the force of F2 on 1. So you can use that using Coulomb's law, which is this expression. And we can just plug in our values, 9 times 10 to the 9th times Q1, which is 1 nanocoulomb, times Q2, which is 2 nanocoulombs. And we use our absolute value signs, and it's over r squared, and we can find r by using the Pythagorean theorem, and it's this triangle right here. So if we do that off to the side, will be 0.02 squared plus 0.03 squared, and the square root of that, which gives you an r value of 0.036. And so you can plug this back here, and you'll get 1.38 times 10 to the negative 5. And now you have to figure out what r hat is. And you just have to use your common sense. Like, since these two charges are alike, that they're going to repel each other according to Coulomb's law. So this is going to go, this middle charge is going to go here. So you have a positive x value and a positive y value, and that can be used, or that can be found by doing cosine hat, or cosine theta I hat plus sine theta j hat, since they're both positive values. And you can find this angle theta by doing the inverse tangent of 2 over 3 opposite over adjacent, and that will give you 33.69 degrees. And now that you know theta, you can plug it back in here to find the total vector component, and the force, the vector component of particle 2 and 1 will be 1.152 times 10 to the negative 5 I hat plus 0.768 times 10 to the negative 5 j hat newtons. And since the particles are symmetrical, 2 and 3 are symmetrical, except, or you can use the same value of the magnitude, but you have to be careful about direction, because since these are like charges, particle 3 is going to push particle 1 in this direction, so you're going to have a negative x value and a positive y value. And so the force of 3 on 1 will be negative 1.152 times 10 to the negative 5 I hat plus 0.768 times 10 to the negative 5 j hat newtons. And so we can plug this value and this value back up here, and then we can solve for the force of particle 4 on 1. And so we can do, I'll write it again, force of 3 on 1 plus the force of 4 on 1. And we know this is 0, and we can plug these values back in, and we will get 1.536 times 10 to the negative 5 plus the force of 4 on 1. And these terms cancel out, the x terms cancel out. So now this gives the force of particle 4 on 1, which will be negative, the negative value of this. So negative 1.536 times 10 to the negative 5. And that will be equal to Coulomb's law. And we're trying to solve for Q4 right here, so we can just isolate Q4 on the side and rearrange everything. And then we can plug back in our values for R and K and Q1. And then when we solve that out, I get 6.83 times 10 to the negative 10 coulombs. And if we want to change that to nanocoulombs, you can use unit conversions and you get 0.68 nanocoulombs. And that is your answer.